Welcome everyone to our first video in the quantitative chemistry unit, where we are going to be mainly talking about Avogadro's hypothesis. This is a pretty big topic that we're going to be getting into. So I've split this video into two parts. And in this part, we are going to be looking at Avogadro's hypothesis. Now, you need to know how to state it, but more importantly, you need to understand the reasoning behind this hypothesis. Why are we talking about it and the implications it had for quantitative chemistry? Now, we haven't talked about quantitative chemistry yet, and quantitative chemistry is where we're using measurements in chemistry. Okay, so anytime we're assigning measurement values in anything chemistry related, that could be quantitative chemistry. This whole topic that we're going to be talking today arises from a problem that has to do with the scale at which chemistry occurs. If you recall back to the nomenclature unit when we talked about ratios of atoms and molecules, and then even think back to earlier grades when you learned about chemical reactions and balancing chemical reactions, you know that chemistry occurs between whole number ratios, simple whole number ratios of atoms and molecules. That's how they react. For example, you never have half a molecule or half an atom reacting. You either have one molecule or you have two molecules or three. So it's all about the numbers of atoms and molecules which are reacting. But simply put, atoms and molecules are too small to be counted. So if we want to carry out a precise chemical reaction, we need to know the numbers of atoms and molecules. But there's no way of doing that by simply counting those atoms and molecules. So this is the fundamental problem. Let me take a moment here to use an analogy, which I will be going back to a few times, which I find can be helpful as we're going through this topic. The analogy I like to use here is talking about candy. So chemistry is often referred to as black box science, where we're trying to understand something about the properties of materials and atoms and molecules, and they're on a scale that's too small to be counted. So imagine I wanted to answer a question about these two candies here, Skittles and M&Ms. And imagine the question I want to know is how many Skittles and how many M&Ms are in each of these bags. But here's the restriction I'm going to put on myself. I'm not allowed to open the bags. So this is analogous to the chemistry problem. We can't see atoms and molecules directly, but we need to be able to count them. I want to know how many candies are in each of these bags, but I can't count them. Now, the reason why this analogy works is because I've got two bags which seem to be similar sizes, but we know something, if you've ever eaten a Skittle or a peanut M&M here, that they are vastly different sizes. So even though they may weigh about the same, and the bags seem to be about the same size, there's probably not the same size of candies in there. You know, if you've ever eaten a peanut M&M, you're probably usually pretty disappointed when you open up the bag because they're so huge that you usually get so few of them. There's probably way more Skittles in here. So this is the same problem as we have in chemistry. I'll be coming back to this analogy when we talk about how we solve this problem throughout this video. So we have this problem. Atoms and molecules are too small to be counted, and chemistry got to a point where chemists really wanted to add precision and really wanted to make chemistry a quantitative science. Not that math is the be-all and end-all, but when you can start adding in quantities, measurements, and mathematics into a science, it really adds in the precision for that science. So in this video, I'm going to talk about how a relative scale was created for atoms. The second part of the solution, which we will see in the second video on the mole, is where we created a conversion factor that allowed us to relate a macroscopic measurement, mass, to something microscopic, the number of particles in some sample. We're going to first deal with the idea of creating a relative scale. Now, before we get into this in detail, let's compare what a relative scale is to an absolute scale. So when we use an electronic balance or any type of balance, and we get some sort of mass in grams, that is an absolute scale where we have some sort of standardized measurement, in this case grams, kilograms, that we use to let us know how much something weighs. So that is an absolute scale. But it turns out for a lot of things, an absolute scale isn't really necessary, especially when we're trying to compare various items. Here's a visual example of a relative scale. Say we just wanted to have a sense, a nice visual sense, of the difference in size of different planets. Now, you could use an absolute scale, and I could tell you the mass of Earth and the mass of Jupiter. But those masses are so huge that the numbers would probably be somewhat meaningless to you. It's much more effective in this case to create to scale models here and put them all beside each other. And then you can see, for example, oh, look, there's Earth right there, and there's Jupiter. And even though you don't know the precise number of times or the precise mass of Jupiter, we can see, relatively speaking, how much smaller Earth is than planets like Jupiter and Saturn. In terms of chemistry, a relative scale is going to be pretty much all we need to do most chemistry. Let's take a look at a real example. Here we have a chemical reaction, and specifically a balanced chemical reaction, which tells us that 2 hydrogen molecules react with 1 oxygen molecule, and that produces 2 water molecules. So here's a synthesis reaction of water. So let's just say, for example, we have 1 kilogram of oxygen gas. And then the question is, okay, we want to carry out this reaction. How much hydrogen gas is going to be needed to react? If we look at this equation, it tells us that we need twice the number of hydrogen molecules as oxygen molecules. So what would happen if we used masses? So we've got 1 kilogram of oxygen. Well, if we try to do this with masses without knowing anything about the relative sizes of the molecules, since oxygen is so much heavier than hydrogen, even if we used 2 kilograms of hydrogen, it still might not be enough hydrogen atoms to react. The only way we can do this precisely is if we know how many times greater an oxygen molecule is than a hydrogen molecule, and then we could possibly figure this out. This gets us to Avogadro's hypothesis. An Italian scientist by the name of Amedeo Avogadro came up with a way for us to develop a relative scale. Now, we might not see the connection directly to our initial problem of counting atoms, but you have to bear with me. What Avogadro came up with was a way to know when we have equal numbers of particles. So, for example, you have 1 container which contains oxygen. You have another container which contains hydrogen. His hypothesis isn't going to tell us how many of each particle, but it will give us a way to know when we have the same number of molecules in each container. Why is that important? Well, if we take 2 samples that each have the same number of particles and we weigh them, that will allow us to know how much a single atom or molecule of one gas weighs compared with another gas. let's go back to our candy example to use a little more concrete idea here. Okay, remember my initial problem. I wanted to know how many candies, individual candies, I had in each of these bags. But I gave myself a restriction and said I can't open the bags. Now, Avogadro's hypothesis is not going to solve my problem, but it's going to help us along in a roundabout way. Let's just say, for the sake of argument, that in each of these bags, there were the same number of candies. Let's just say 20 candies here and 20 candies here. If we knew for sure there were the same number of candies and we weighed them, we would probably find a difference in weight. Well, if you've ever had a Skittles and a peanut M&M, you know that a peanut M&M is quite large and a Skittles is quite small. So if we have 20 of each, the M&M bag is going to weigh a lot more than the Skittle bag. Let's say, for the sake of our example, the M&M bag weighed twice as much as the Skittle bag. If the whole bag weighs twice as much and we have the same number of candies in each bag, that would tell us that one M&M weighs twice as much as one Skittle. So without even opening the bags, as long as we know that we have the same number, as in we're comparing like to like, the same number of particles, we can know something about the relative weights of each of the candies. Okay, let's switch back to chemistry now and go through the hypothesis in more detail. So here's Avogadro's hypothesis formally stated. Equal volumes of gases at the same temperature and pressure contain equal numbers of particles. So let's rephrase that. Remember, Avogadro's hypothesis gives us a way to know when we have the same number of particles in two different containers. So how do we know that? Well, if we have two different substances and they're gases, and we put them in equal volume containers, and we adjust the temperature and pressure so that in each of those containers, the temperature and pressure are the same, then we will know that we have the same number of particles in each of those containers. Let's talk about the reasoning behind Avogadro's hypothesis. Why does it work? So the first part of his hypothesis says the substances we have to be comparing here must be gases. Why? Well, in the gas state, particles are not attracted to each other. There's no intermolecular forces. Now, part of gas theory with chemistry shows us that the volume of a gas is controlled by three different variables. The temperature. So if you increase the temperature of a gas, it increases the volume. Basically how a hot air balloon works. Second variable, pressure. If you increase the pressure, that decreases the volume of a gas. Imagine just pushing down on a syringe that's capped at the end. And finally, the number of particles. If you put more atoms or molecules of a gas in a container, that will increase the size if everything else is equal. So these three things affect the volume of a gas. And so that's why we see those three variables in Avogadro's hypothesis. So if we keep the temperature, pressure, and volume equal between two different samples, it follows from what we know about gases that they must have the same number of particles. So just as I showed with the Skittles and the M&Ms, if we have two samples and we know we have the same number of particles in each of those samples, we can weigh those samples and learn something about the relative weights of the individual particles. Let's take 4 of the basic gases here: hydrogen, helium, neon, and oxygen. So as scientists started to put Avogadro's hypothesis into practice and looked at the relative weights of equal volumes of gases at the same temperature and pressure, what did they find? Well, they found results like this. Oxygen weighed 16 more times than hydrogen. If we compared helium and oxygen, helium was 4 times less than oxygen. Nitrogen, 14 times more than hydrogen. And after weighing more and more gases, they found that hydrogen was the lightest element. So on a relative scale, the easiest way to develop a relative scale is to assign the smallest value to be 1. So hydrogen was assigned a relative weight of 1. Look at the periodic table. What do you see? You see an atomic mass unit very close to 1. Okay, it's not a coincidence there. So hydrogen was assigned a value of 1. Oxygen, a value of 16. Because there's equal volumes of hydrogen and oxygen weighed 16 more times than hydrogen. And scientists just began comparing different gases to develop a relative atomic scale. And as technology improved, they were able to test and compare more and more elements. Let's go back to the example I gave earlier, where we were synthesizing water from hydrogen and oxygen. And remember our problem. We know that we need twice as many hydrogens as oxygens, but we can't count those atoms or molecules directly. We can only weigh them and know something about the mass of one gas and the mass of another. So I'll leave you with a problem here, and I want you to try to solve it. And I'll give you 2 hints to get started. If we have 1 kilogram of oxygen gas, how much hydrogen is needed to react with that oxygen gas? So remember 2 things. We need twice as many hydrogen molecules as oxygens. And now that we've developed a relative scale, we know that 1 oxygen molecule weighs 16 times more than a hydrogen.